Now in this lecture we find out the area of the green shape. In the drawing we have a circle inside a quarter circle. We know that the radius of this small circle is equal to the square root of 2 units in its length. Again, our mission is to find out the area of this green shape. So first of all, we'll define the relevant points to this question with letters. We define this point as A, we define this point as B. This point is the center of the quarter circle or the center of the big circle. We define the center of the big circle, this point as O. We define this point as C. We define this point as D. This point is the touching point between the small circle and the big semicircle. We define the touching point as E. And finally, we define the center of this small circle as F. In the next step, we'll join points F and C together by a straight line. What is the definition of line segment FC? Line segment FC starts from point F, that is the center of the small circle, and ends at point C, that is a point on the small circle itself. This is exactly the definition of a radius. So FC is the radius of this small circle that is equal to the square root of 2 units in its length according to what is given as the question. So here we can implement rule 1. I'll repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle and we have this is tangent AB, that is tangent to this circle, and this point M. Point M is the point of tendency of the tangent AB with this circle. And we have the radius OM that is equal to R, that is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees. If this angle equals to 90 degrees, so we need to this rule 1. So we can actually implement rule 1 in our drawing. Why? Because in our drawing we have the radius FC that is drawn to point C, that is the point of tendency of tangent OD with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius CF. If OD is perpendicular to CF, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius FB of the small circle that is drawn to point B, that is the point of tendency of tangent AO with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius BF. If AO is perpendicular to BF, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the sum rule, rule 1. So inside this small quadrilateral FBOC, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of this fourth angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this missing angle, this missing fourth angle, must be equal to 90 degrees in its size. Again, in order to complete the sum of the angles inside this whole quadrilateral FBOC to 360 degrees, the missing angle here must be equal to 90 degrees in its size. So I'm sure you found out that inside quadrilateral FBOC we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral FBOC is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. So in rectangle FBOC, side FB must be equal to the opposite side OC. But FB equals to the square root of 2 units, therefore OC must be also equal to the square root of 2 units in its length. Likewise, according to the same rule, side FC must be equal to side BO in rectangle FBOC. But FC equals to square root of 2, therefore BO must be also equal to the square root of 2 units in its length. So actually found out that this small quadrilateral BFOC is not a rectangle but a square. Why? Because of the fact that all of its sides of this quadrilateral are equal to each other. Its side is equal to the square root of 2 units in its length, therefore quadrilateral BFOC is a square. In the next step, we join points O and F together by a straight line. By joining points O and F, we created the right quadrilateral B, the right triangle OFB. So inside we have here the right triangle OBF. In the right triangle OBF, side BF equals to side BO. They are both equal to the square root of 2 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle there are equal angles. So those 2 angles that are located in front of those 2 equal sides must be also equal to each other. So if we define the size of this angle as alpha, then the other angle must be also equal to alpha because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees, and especially it is true in the right triangle BFO. So which angles we have inside the right triangle BFO? We have this angle that is 90 degrees, this angle that is alpha, the other angle that is also alpha. So 90 degrees plus 2 alpha, in total they must be equal to 180 degrees. I write it down. Here we subtract 90 degrees from the equation and we get that 2 alpha equals to 180 degrees minus 90 degrees is equals to 90 degrees. Here we divide this equation by 2 and finally we get that the missing angle alpha equals to 90 degrees over 2, that is 45 degrees. So actually this is angle alpha that is equal to 45 degrees in its size. And this is also angle alpha is equal to 45 degrees. In the next step, we will implement the Pythagoras theorem in the right triangle BFO. Here by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equal to the sum of the squares of the perpendiculars. The hypotenuse on the right triangle BFO is OF, therefore the square of the hypotenuse is OF squared. and it must be equal to BF square plus BO square. Repeat again, in the right triangle BF4, according to the Pythagoras theorem, OF square equals to BF square plus BO square. So OF square, that is the square of the hypotenuse, equals to BF square. BF is square root of 2, therefore BF square is square root of 2 squared, that is 2, plus BO square. BO is also square root of 2, therefore BO square is square root of 2 squared, that is 2. So in conclusion, we know that OF square equals to 2 plus 2, that is 4. OF square equals to 4. Here we take a root out of this equation, and finally we get that OF, the length of the hypotenuse OF, it is equals to the square root of 2, that is 2. So here, the hypotenuse OF is equals to 2 units in its length. So in the next step, I'll present to you a new rule, and we'll implement the new rule in our drawing. According to the new rule, rule 9, if two circles touch each other internally, then the straight line that connects their centers together must pass through their touching point. So in the drawing we have two circles. This small circle is located inside the big circle, and therefore we have here an internal notch between those two circles. That is to say they are touching each other internally at point P. So, and whenever you have an internal notch between two circles, you can implement this rule, rule 9. So according to rule 9, the straight line that connects their centers together must pass through their touching point. The center of this big circle is here at point O, the center of this small circle is here at point M, and the straight line that connects their centers together is the straight line OM. And according to this rule, rule 9, the straight line OM must pass through the touching point, that is actually point P. So OMP is one straight line. The straight line OM must pass through point P, that is to say OMP is one straight line. Okay? So we can actually implement rule 9 in our drawing. Why? Because of the fact that this small circle is located inside the big quarter circle, and they touch each other internally at point E. For that reason, we can implement here rule 9. The center of the big circle or the big quarter circle is here at point O. The center of this small circle is here at point F. And the straight line that connects the centers together is the straight line OF. And according to rule 9, the straight line OF must pass through point E, that is their touching point. Or OFE is one straight line. Again, OFE is one straight line. So when we extend line segment OF, it must pass through point E according to rule 9. Yeah. OFE passes through point E, that is the touching point between this small circle and the big quarter circle. So actually, according to rule 9, line segment OFE is one straight line. Okay, write it down. OFE is one straight line. So we know that OFE is a straight line. What is the other definition of the straight line OFE? Actually, the straight line OFE starts from point O, that is the center of the quarter circle and also the center of the big circle, and n set point E, this is a point on the big circle itself. And this is exactly the definition of a radius. So OFE is the radius of the big circle. So we define the radius of the big circle as capital R. So write it down, capital R is the radius of the big circle. So capital R equals to OFE. This is the radius of the big circle. What is the length of OFE? That is the radius of the big circle. First of all, we find out the length of line segment FE. Line segment FE starts from point F, that is the center of this small circle, and ends at point E, that is the point on the small circle itself. This is exactly the definition of a radius. Therefore, FE is the radius of this small circle that equals to the square root of 2 units in its length, according to what is given as the question. So we know that OFE, because of the fact that OFE is one straight line, it means that OFE, the straight line OFE equals to OF plus FE. Okay, OF equals to OF plus FE. So OF equals to OF, that is 2, plus FE, that is square root of 2. So in conclusion, we found out that capital R equals to 2 plus square root of 2. The radius of the big circle capital R equals to 2 plus square root of 2 units. We define the intersection point between the radius OFE and this small circle as H. We know that OFE is one straight line, therefore HFE is also a one straight line, so HFE is a straight line. HFE is a straight line that touches the small circle at points H and E, and therefore any straight line that touches the circle at 2 points must be a chord. So we know that HFE is a chord, but HFE is a chord that passes from point F, that is the center of the small circle, and we know that any chord that passes from the center of a circle must be the diameter of the circle. So therefore HFE is the diameter of the circle, diameter of the small circle, of course. And we know that the diameter of any circle bisects the circle into two halves. The diameter HFE bisects the circle into two halves. So this is the first half, and this is the second half. Each half is defined as a semicircle, of course. So this shape is a semicircle. Or we can define it as the small semicircle. Okay? The small semicircle. Okay? So in the next step, I will present to you the notion of a sector. What is a sector? A sector is part of a circle. This is a circle, and the green shape AOB is a sector. If you look at this circle as a cake, then this sector is one slice of this cake. Okay? And the green sector AOB consists of two legs. The first leg is AO, and the second leg is BO. Both legs of the green sector AOB are the radii of this circle that is equal to R. And the angle between the legs AO and BO of the green sector AOB is theta. And what is the area of this sector AOB? The area of sector AOB equals to the area of the circle that contains the sector, that is pi r squared, times the angle between the legs of the sector, that is theta, over 360 degrees. So in conclusion, you can say that the area of any sector equals to the area of the circle that contains the sector over the angle between the legs of the sector over 360 degrees. Again, the area of any sector equals to the area of the circle that contains the sector times the angle between the legs of the sector over 360 degrees. So, repeat again that our mission is to find out the area of this green shape. So, what is the area of the green shape? From the drawing, it is very easy to see that the area of the green shape in total will be equal to the area of the big sector AOE the rounded line above AOE is the same for a sector, it means sector AOE, and the squared brackets is the same for the area, so in total this expression equals to, it means that the area of sector AOE, so the area of the green shape equals to the area of the big sector AOE minus the area of the small semicircle, minus the area of shape HBO, minus the area of the orange shape HBO. Repeat again that the area of this green shape in total equals to the area of the big sector AOE minus the area of this small semicircle minus the area of this orange shape BHO. The area of the green shape equals to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape HBO. Okay, so first of all we find out the area of the big sector AOE. The big sector AOE is part of the big circle, and we know that the area of any sector equals to the area of the circle that contains the sector. The big circle contains the big sector AOE, and we know that the area of the big circle will be equal to pi times capital R squared times the angle between the legs of this sector AOE. This is the angle between the legs of sector AOE. This angle equals to 45 degrees in its side, so it is 45 degrees over 360 degrees. So the area of the big sector AOE equals to pi times capital R squared. We only found out that capital R equals to 2 plus square root of 2, therefore capital R squared equals to 2 plus square root of 2 squared times 45 degrees over 360 degrees, it is 1 over 8. So you have to divide the area of the big circle by 8. So the area of the big circle AO equals to pi times 2 plus square root of 2 square. 2 plus square root of 2 square, according to the algebraic identity that a plus b square equals to a square plus b square plus 2 times ab. 2 plus square root of 2 square will be equal to 2 square, that is 4, plus square root of 2 square, that is 2, plus 2 times 2 times square root of 2, all divided by 8. So it is equals to pi, and inside the brackets we have 4 plus 2, that is 6, plus 2 times 2 is 4, so in total this expression will be equal to 4 times square root of 2, all divided by 8. Here we divide both the numerator and the denominator of this expression by 2, and we get that we have here pi, inside the brackets we have 6. 6 over 2 is 3, plus 4 times square root of 2 over 2 is 2 times square root of 2, and we have to divide the denominator 8 by 2. 8 over 2 is 4. So in conclusion, we found out that the area of the big sector AOE, in total it is equals to pi times 3 plus 2 times square root of 2 over 4 square units. In the next step, we find out the area of the small semicircle. Repeat again, we find out the area of this small semicircle. You should remember that the small semicircle is half of the small circle. And we know that the area of the circle, the area of this small circle, is equals to pi r square. Again, the area of the small circle equals to pi r square, and when we will divide the area of the small circle by 2, we get the area of the small semicircle. So it is pi, and r is square root of 2, therefore r square is square root of 2 squared, that is 2, divided by 2. 2 over 2 is 1, so we'll have to leave pi. In conclusion, we found out that the area of the small semicircle is equals to pi square units. Finally, we have to find out also the area of this orange shape. What is the area of the orange shape? The orange shape HBO. What is the area of the orange shape HBO? From the drawing, it is very easy to see that the area of the orange shape equals to the area of the right triangle FBO minus the area of the small sector FBH. Repeat again, the area of the orange shape HBO equals to the area of the right triangle FBO minus the area of the small sector FBH. The small sector belongs to the small circle, of course. So, first of all, we find out the area of the right triangle FBO. If this is the right triangle FBO, you can see that the two perpendiculars, they are equal to each other. Both of them are equal to the square root of 2. The area of any triangle equals to the base of the triangle times the height to the base over 2. In our case, in triangle FBO, the base equals to the height, they are both equal to the square root of 2 units. So the base is square root of 2, and the height is also square root of 2 divided by 2. Square root of 2 times square root of 2 is 2, and 2 over 2 is 1. So in conclusion, we found out that the area of the right triangle FBO is equal to 1 square units. In the next step, we find out the area of the small sector FBH. The small sector FBH is part of the small circle, and we know that the area of any sector equals to the area of the circle that contains the sector. The small sector FBH is contained by the small circle, and the area of the small circle equals to pi r squared times the angle between the legs of the sector. The angle between the legs of this sector FBH is here we have this angle equals to 45 degrees. So it is 45 degrees over 360 degrees. So the area of the small circle equals to pi. R is square root of 2, therefore r squared is square root of 2 squared, that is 2. So in total, the area of the small circle equals to 2 pi times 45 degrees over 360 degrees, it is 1 over 8. So we divide the area 2 pi of the small circle by 8. Here we divide both the numerator and the denominator of this expression by 2. 2 pi over 2 is pi, and 8 over 2 is 4. So in conclusion, we found out that the area of the small sector FBH is equal to pi over 4 square units. So in total, the area of the small sector HBO, the area of the orange sector, the area of the orange shape HBO is equal to the area of the right triangle FBO, that is 1, minus the area of the small sector FBH, that is pi over 4. Repeat again that the area of the orange shape HBO, in total it is equal to 1 minus pi over 4 square units. Repeat again that the area of the green shape is equal to the area of the big sector AOE that we have already found out, minus the area of the small semicircle that we also have already found out, minus the area of this orange shape HBO that we have already found out. Repeat again. The area of the green shape equals to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape HBO. So we have already found out that the area of the big sector AOE is equals to pi times 3 plus 2 times square root of 2 over 4 square units minus the area of the small circle, the small semicircle is equals to pi square units minus the area of the orange shape HBO that is equals to 1 minus pi over 4 square units. So this expression, the value of this expression is the area of the green shape. So we just simplify this expression in order to find the area of the green shape in terms of numbers. So here we open the brackets and we get here 3 times pi is 3 pi plus 2 times square root of 2 times pi divided by 4 minus pi. Here we have minus before the brackets. So after we open the brackets here, we get minus 1 and we have here minus times minus is plus. So it will be in total minus 1 plus pi over 4. So we get here 3 pi plus 2 times square root of 2 pi over 4. And we have here minus pi plus pi over 4 is minus 3/4 pi. So it is minus 3 pi over 4. And we have here also minus 1. Here we multiply minus 1 by 4 and then we divide it by 4 in order to become a factor with the other two expressions. So minus 1 times 4 is minus 4 divided by 4. So here we have 3 pi minus 3 pi is 0. So after we cancel 3 pi, we left only with 2 times square root of 2 pi minus 4 over 4. Here we divide both the numerator and the denominator of this expression by 2, and we get the 2 times square root of 2 pi over 2 is square root of 2 times pi, minus 4 over 2 is minus 2, and we have to divide the denominator 4 also by 2. 4 over 2 is 2. So in conclusion, we found out that the area of the green shape in total, it is equals to either square root of 2 pi minus 2 over 2 square units, or in terms of numbers, it is equals to 2.114 square units. Repeat again. The area of this green shape equals to either square root of 2 times pi minus 2 over 2 square units, or in terms of numbers, the area of this green shape equals to 2.114 square units. So in the next step, I will summarize the lecture. this lecture we found out the area of this green shape. In the drawing we have a circle inside this quarter circle. In addition, we know that the radius of this small circle equals to the square root of 2 units in its length. Again, our mission is to find out the area of this green shape. So first of all, we defined the relevant points to this question with letters. We define this point as A, we define this point as B. This point is the center of the big quarter circle and also the big of the circle, the center of the big circle also. So we define the center of the big circle, this point as O. We define this point as C, we define this point as D. This point is the touching point between this small circle and the big quarter circle. We define the touching point as E. And finally we defined the center of this small circle as F. Then we join points F and C together by a straight line. What is the definition of line segment FC? Line segment FC starts from point F, that is the center of the small circle, and ends at point C, that is the point on the small circle itself. This is exactly the definition of a radius. Therefore, FC is the radius of this small circle that is equal to the square root of 2 units in its length. We can implement here rule 1 according to rule 1 because of the fact that the radius FC is drawn to point C, that is the point of tendency of tangent OD with this small circle. Therefore, and so because of the fact that the radius FC is drawn to point C, then tangent OD will be perpendicular to the radius CF. If OD is perpendicular to CF, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius FB that is drawn, the radius FB of the small circle, of course. The radius FB is drawn to point B, that is the point of tendency of tangent AO with this small circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius BF. If AO is perpendicular to BF, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. This is rule 1. So inside the small quadrilateral BFOC, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of this fourth angle. In total, the sum of those 4 angles, they must be equal in total to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle must be equal to 90 degrees. Okay? So inside the small quadrilateral FBOC, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this small quadrilateral FBOC as a rectangle. And you also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle BFOC, side BF must be equal to the opposite side OC. But BF equals to the square root of 2, therefore C must be also equal to the square root of 2 units in its length. Likewise, according to the same rule, in rectangle BFOC, side FC must be equal to the opposite side BO. But FC equals to the square root of 2, therefore BO must be also equal to the square root of 2 units in its length. So we should find out that the quadrilateral BFOC is not a rectangle but a square. Why? Because all of its sides are equal to each other. Each side of this square is equal to the square root of 2 units in its length. In the next step, we join points F and C together by a straight line. I repeat again, we join points F and C together. We join points F and O together by a straight line. We join those 2 points by a straight line. By joining points F and O, we created the right triangle FBO. In the right triangle FBO, those 2 sides equals to the square root of 2 units in its length, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle there are equal angles. So those 2 angles that are located in front of those 2 equal sides must be equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. And we also know that in any triangle, the sum of the angles must be equal to 180 degrees. And especially it is true in the right triangle BFO. So which angles we have in the right triangle BFO? We have alpha plus alpha, that is 2 alpha plus 90 degrees. In total, they must be equal to 180 degrees. Again, 90 degrees plus 2 alpha must be equal to 180 degrees according to the rule that I mentioned. Here we subtract 90 degrees from this equation, and we found out that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. Here we divided this equation by 2, and finally found out that the missing angle alpha equals to 90 degrees over 2, that is 45 degrees. So this angle alpha equals to 45 degrees, and this is also angle alpha that is equals to 45 degrees in its size. In the next step, I presented to you a new rule. We implemented the new rule in our drawing. According to Rule 9, if two circles touch each other internally, then the straight line that connects their centers together must pass through their touching point. In the drawing, we have an internal notch between those two circles. Because of the fact that the small circle is located inside the big circle and they touch each other internally, you can say that there is an internal notch between those two circles, and whenever you have an internal notch between two circles, you can implement Rule 9. So the center of the big circle is 0.0. The center of this small circle is 0.m. The straight line that connects their centers together is the straight line OM. And according to this rule 9, the straight line OM must pass through point P, that is their touching point. Again, the straight line OM must pass through point P, that is their touching point, or OMP is one straight line. OMP is one straight line. We can actually implement Rule 9 in our drawing. Why? Because in our drawing, the small circle is located inside this big quarter circle, and those two circles touch each other internally at point E. For that reason, or for those reasons, we can implement Rule 9. The center of the big circle and the big quarter circle is 0.0. The center of this small circle is 0.f, and the straight line that connects the centers together is the straight line OF. And according to Rule 9, the straight line OF must pass through point E, that is their touching point. Again, the straight line OF must pass through point E, that is their touching point. Or OFE is one straight line. Again, OFE is one straight line. So you can write here that OFE is one straight line according to Rule 9. But what is the other definition of the straight line OFE? The straight line OFE starts from point O, that is the center of the big circle, and ends at point E, that is the point of the big circle itself. This is exactly the definition of a radius. Therefore, OFE is also the radius of the big circle. So we define the radius of the big circle as capital R. Here, capital R is the radius of the big circle. So we found out that capital R, the radius of the big circle capital R, equals to OFE. What is the length of line segment FE? Line segment FE starts from point F, that is the center of this small circle, and ends at point E, that is the point of the small circle itself. This is exactly the definition of a radius. Therefore, line segment FE is the radius of this small circle, that is equal to the square root of 2 units according to what is given as the question. So, because of the fact that OFE is one straight line, it means that the length of OFE, it must be equal to OF plus FE. Again, OFE equals to OF plus FE. OF is 2 and FE is square root of 2. So in total, OFE equals to 2 plus square root of 2. So from this equation, we derive that the radius of the big circle capital R equals to 2 plus square root of 2. The radius of the big circle capital R equals to 2 plus square root of 2 units. So we found out that OFE is one straight line. We defined the intersection point between the straight line OFE and this small circle, this point as H. if OFE is one straight line, then HFE must be also one straight line because HFE is part of OFE. So we know that HFE is a straight line that touches this small circle at point H and then point E. And any straight line that touches the circle at 2 points must be a chord. So HFE is a chord of this small circle, but it is a special chord that passes through point F, that is the center of this small circle. And we know that any chord that passes through the center of a circle must be in the diameter of the circle. So HFE is the diameter of the small circle. HFE is the diameter of the small circle. And we know that the diameter of any circle bisects the circle into two halves. Here HFE bisects the circle into two halves. This is the first half and this is the second half. Half of a circle is defined as a semicircle. So this shape is the small semicircle and the other shape is also the small semicircle. So we found out in conclusion that this shape is a small semicircle. Then I presented to you the notion of a sector. A sector is part of a circle. This is a circle and the green shape AOB is a sector. If we look at this circle as a cake, then the sector AOB is one slice of this cake. Okay, so the green sector AOB consists of two legs, the legs AO, the leg AO and the leg BO. Those two legs, they are both the radii of this circle that is equal to R, and the angle between the legs AO and BO of the green sector AOB is theta. And the area of this green sector AOB equals to the area of the circle that contains the sector. The area of this circle is pi r square times the angle between the legs of the sector, that is theta, over 360 degrees. In conclusion, we found out that the area of any sector equals to the area of the circle that contains the sector times the angle between the legs of the sector over 360 degrees. Then I repeat again that the area of the green shape equals to the area of the big sector AOE minus the area of this small semicircle minus the area of this orange shape HBO. And the area of the green shape in total it is equal to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape HBO. What is the area of the big sector AOE? The area of any sector equals to the area of the circle that contains the sector. This big sector AOE is contained by the big circle. So the area of the big circle is pi times capital R square times the angle between the legs of this big sector AOE. This is the angle between the legs, that is equal to 45 degrees over 360 degrees. So it is pi r squared, the area of the big circle, times 45 degrees, that is the angle between the legs of the big sector AOE over 360 degrees. So what is the value of pi times capital R squared? Capital R equals to 2 plus square root of 2, therefore capital R squared equals to 2 plus square root of 2 squared, and times 45 degrees over 360 degrees. 45 degrees over 360 degrees is 1 over 8, so we have to divide the area of the big circle by 8. So what is the value of this expression? It is equals to pi, and 2 plus square root of 2 squared equals to 2 squared, that is 4, plus square root of 2 squared, that is 2, plus 2 times square root of 2. All divided by 8. So We have here pi, and inside the brackets we have 4 plus 2, that is 6, and 2 times 2 is 4, so in total this expression equals to 4 times square root of 2, all divided by 8. Here we divided both the numerator and the denominator of this expression by 2, and we got that this expression after we divided by 2 will be equal to pi, and 6 over 2 is 3, and 4 times square root of 2 over 2 is 2 times square root of 2, and we have to divide the denominator 8 also by 2, 8 over 2 is 4. So in conclusion, we found out that the area of the big sector is equal to pi times 3 plus 2 times square root of 2 over 4 square units. In the next step, we found out the area of the small semicircle. The area of this small semicircle. The area of the small semicircle is half of the area of the small circle, of course. Again, the area of the small semicircle is the half of the area of the small circle. The area of the small circle is pi r square, and when we divide the area of the small circle by 2, we'll get the area of the small semicircle. So in total, the area of the small semicircle equals to pi r square over 2. R is square root of 2, therefore r square is square root of 2 square, that is 2. So the area of the small circle is 2 pi, and when we divide the area of the small circle by 2, we get the area of the small semicircle. 2 over 2 is 1, so we found out that the area of the small semicircle it is equal to pi square units. And finally, we found out the area of this orange shape HBO. From the drawing, it is very easy to see that the area of the orange shape HBO in total it is equal to the area of the right triangle FBO minus the area of this small sector FBH. Again, the area of the right triangle FBO minus the area of this small sector FBH, it is equal to the area of the orange shape HBO. Okay, again, the area of the orange shape HBO equals to the area of the small sector FBO. The small sector FBO is, of course, part of the small circle minus the area, again, the area of the orange shape HBO equals to the area of the right triangle FBO minus the area of the small sector minus the area of the small sector FBH. The small sector FBH is part of the small circle, of course. So what is the area of the right triangle FBO? The area of any triangle equals to the base of the triangle times the height to the base over 2. Here, in the right triangle FBO, BF equals to BO. So the height equals to the base. They are both equal to the square root of 2 units. So the base is square root of 2 and the height is also square root of 2 divided by 2. Square root of 2 times square root of 2 is 2 and 2 over 2 is 1. So in conclusion, we found out that the area of this right triangle FBO is equal to 1 square unit. And we have to subtract from the area of the right triangle FBO the area of this small sector FBH. And because of the fact that the small sector FBH is part of the small circle, and therefore the area of the small sector FBH equals to the area of the circle that contains the sector. The small circle contains the small sector FBH, and the area of the small circle is pi r square times the angle between the legs of this small sector FBH. The angle between the legs of this small sector FBH is 45 degrees. So it is 45 degrees over 360 degrees. R is square root of 2, therefore R square is square root of 2 squared, that is 2. So in total, the area of the small circle pi r square is 2 pi times 45 degrees over 360 degrees. 45 degrees over 360 degrees, it is 1 over 8. So we have to divide the area 2 pi by 8. Here we divided both the numerator and the denominator of this expression by 2. 2 pi over 2 is pi, and 8 over 2 is 4. So in conclusion, we found out that the area of this small sector FBH is pi over 4 square units. And in total, the area of the orange shape equals to the area of the right triangle FBO, that is 1, minus the area of the small sector FBH, that is pi over 4. So in total, the area of the orange shape FBO is 1 minus pi over 4 square units. Again, our mission is to find out the area of this green shape. The area of the green shape in total equals to the area of the big sector AOE minus the area of this small semicircle minus the area of this orange shape HBO. Repeat again. The area of the green shape in total it is equals to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape HBO. We have already found out that the area of the big sector AOE is pi times 3 plus 2 times square root of 2 over 4 square units minus the area of the small semicircle. We have already found out that the area of the small semicircle equals to pi square units minus the area of the orange shape HBO. We have already found out that the area of the orange shape HBO it is equal to 1 minus pi over 4 square units. So the value of this expression it is equal to the area of the green shape, the area that we are looking for. So we just simplify this expression in order to find the area of the green shape in terms of numbers. We open the brackets here. Pi times 3 is 3 pi plus pi times 2 times root of 2 is 2 times root of 2 times pi divided by 4. And we have here minus pi, here minus pi, and we open the brackets here, we have minus before the brackets, so this expression after we open the brackets will be equal to minus 1, and we have minus times minus, that is plus. So in total, it will be equal to minus 1 plus pi over 4. So we have here 3 pi plus 2 times square root of 2 times pi over 4, and we have here pi minus pi plus pi over 4 is minus 3/4 pi, and we have here minus 1. We multiply minus 1 by 4 and then we divided it by 4 in order to have a common factor with the other two expressions. So minus 1 times 4 is minus 4 divided by 4. So here we have 3 pi minus 3 pi that is 0. So after we cancel 3 pi we left only with 2 times root of 2 pi minus 4 over 4. Here we divided both the numerator and the denominator of this expression by 2. 2 times root of 2 pi over 2 is square root of 2 pi, and minus 4 over 2 is minus 2, and we have to divide the denominator of 4 also by 2. 4 over 2 is 2. So in conclusion, we found out that the area of this green shape is equals to either square root of 2 times pi minus 2 over 2 square units, or in terms of numbers, the area of this green shape it is equals to 2.114 square units. Okay, thank you very much.